Okay, so today we will be working with the second derivative, and we're still going to be working on our chart here for the connections between a graph of f, its derivative f prime, and its second derivative f double prime. And so last time we filled out the information in the green, and to find out the information in the green, which is where f is increasing, decreasing, has local maxes and local mins and critical points, we worked with the first derivative. Information in green, you worked with the first derivative. And the directions for what to do were there. Today, we are going to be working in the purple section with the second derivative. Okay, let's go back to our notes. Okay, so the big idea is to talk about the concavity of a function f. And what we're going to be discussing really is that when f is increasing at an increasing rate, so not only is f increasing, f prime. So not only, no, this was f. Not only is f increasing, but the rate at which f increases is also increasing. So say, for example, that f was 1, and then 2, and then 4, and then 7. This would be an example of a function that's increasing at an increasing rate. Because notice that my values are increasing. They're getting bigger. But not only that, see, in the first instance, I increased by 1. In the second instance, I increased by 2. And the third time, I increased by 3. Look at that. This is also increasing. So not only do I increase, but the rate at which I increase is increasing as well. And what happens when a function does that, if I just plot the points 0, 1, 1, 2, 2, 4, and then the next one 7, what happens is the concavity of the curve will be curvy up, will be concave up. Also, if you look at the slopes of the tangent lines are getting larger. So this means that f prime is increasing. So a function f is concave up if f increases at an increasing rate, which means that f prime is increasing. On the other hand, if my values go down, so my f values are, so I'm still going to increase. But if the rate at which I increase is decreasing, then my function is concave down. So if my function, let's say that my points which were increasing, let's say that my values are 1, and then I jump up 3 to 4. And now the next time I only jump up 2 to 6. And then the next time I only jump up 1 and I get 7. So this time I went up 3, then 2, then 1. Notice that my rate of increase is decreasing. This would be concave down. And so if I were to graph these values, 1, 4, 6, 7, notice my values increase, but now my curve is curvy down. And so this means f prime is decreasing, and my function f is concave down. Okay. And then finally, we have the definition of inflection point. An inflection point is a point in which the concavity of a curve changes. And so I change from increasing at an increasing rate to increasing at a decreasing rate, perhaps. Also, conversely, f doesn't have to be increasing. F could be decreasing. But if f decreases at an increasing rate, then f is concave up. All right, let's fill out our chart. Things should make sense when we fill out the chart. So when f, this is the second column here where I have the word increasing. This is, remember, my f prime column. So if f prime is increasing, then my function f is concave up. And if f prime is decreasing, then that means that my function f is concave down. All right, so I'm telling you that there's something to do with the second derivative here. And what does this have to do with the second derivative? Well, let's see here. The second derivative is the derivative of the first derivative. So in this column, here I have f, okay, prime. Sorry, this is the column for f prime. What I'm interested in knowing when f prime is increasing. And we just spent a few days talking about how to find when something is increasing. A function increases when its derivative is positive, right? Didn't we just write that down in the green boxes? A function is increasing when f prime is positive. So what if that function happens to be f prime? What about when is f prime increasing? Well, f prime would be increasing when its derivative, f double prime, is positive. So f prime increases when its derivative, f double prime, is positive. And f prime decreases when its second derivative is negative. And then we have inflection point. An inflection point is when you change concavity. So to change concavity, to go from concave up to concave down, then my f prime must change from increasing to decreasing. That means I have a local maximum. If I change from increasing to decreasing, then that's a local maximum. On the other hand, if I change from decreasing to increasing, that would be a local minimum. In either of these cases, I changed from increasing to decreasing or decreasing to increasing, and so I changed concavity, and that's the definition of inflection point. Okay, so now I'm again wondering what's going to happen in the second derivative if my first derivative has a maximum. Well, we already learned about what happens. We know that if a function f has a maximum, then its derivative changes from positive to negative. So if what the function is that you're talking about happens to be the first derivative, then its derivative, the second derivative, changes from positive to negative. Conversely, the second derivative will have, the second derivative changing from negative to positive will mean that the first derivative has a minimum. But in either case, in the original function f, we have an inflection point. And so we have completed our chart. And down here at the bottom, I've described how we're going to use the chart. So anytime you need to know something about f that's in purple, so where is f concave up, where is f concave down, or where is f have an inflection point, then you need to work in the second derivative where the sign chart parts are. So the instructions say find the second derivative, find the critical points of the second derivative, and do a sign chart. So it's the same instructions, it's just on the second derivative instead of the first derivative. All right, so let's do an example. So in these two examples I have, we're going to find the points of inflection and discuss the concavity. By discussing the concavity, I really just explain where a function is concave up and concave down. All right, so direction number one says to find the second derivative. Before I find the second derivative, I have to find the first derivative. Now I take the derivative of the first derivative to get the second derivative. And this is going to be 24x plus 48. Now I find the critical points here. So I'm going to set this equal to 0. And I get negative 2 as my critical point. Now I'm going to set up a sign chart. I'm going to label my sign chart f double prime because I care about this, or maybe I should call it y double prime, because I'm caring about the sign of the second derivative. All right, so at negative 2, I have the critical point. If I plug in 0, I get positive. And if I plug in -3, I would get negative. And so this means that my function y is concave down when y double prime is negative. And that would be on the interval -∞ to -2. Also, y is concave up when the second derivative y double prime is positive. And that would be on the interval 2 to infinity, as read on my sign chart. Finally, y has a point of inflection where the concavity changes, and that would be at x equals -2. All right, so I've essentially just answered the same sorts of questions that we've been answering for the past few days, but I've done it using the second derivative, and it's been about concave up and concave down rather than increasing and decreasing. And instead of maxes and mins, they're called critical points, or not critical points, inflection points. All right, let's do example 2. It has some trigonometry in it. I need to start by, the instructions are the same. I'm to discuss the concavity and to find inflection points. And so to do that, I work with the purple part of the chart, and I work in the second derivative. So I'm going to start by taking the first derivative, and now I take the derivative of the first derivative, and I get 2 sine of x. I set this equal to 0 to find those critical points, and so I need to know when sine is 0. This happens at multiples of pi. All right, and notice that I have a domain restriction here. That's just because this problem would go on forever if not. And so I'm going to only look between 0 and 3 pi. I got 0 and 3 pi, but those are endpoints, so I don't need to worry about them. And then I have pi and 2 pi. And this, again, I'm going to label as y double prime to remind myself that I'm doing a sign chart on the second derivative now. And so I plug values into the second derivative equation to figure out if I have positive or negative. All right, so here between 0 and pi, let's plug in pi halves. So if I plug pi halves into the second derivative, I get 2 times the sine of pi halves. The sine of pi halves is 1, so this is positive. Between pi and 2 pi, that's in quadrants 3 and 4. In quadrants 3 and 4, those are below the x-axis, and that's where sine is negative. And so I know that my second derivative, which is just 2 sine of x, will be negative there. And then lastly, between 2 pi and 3 pi, I come back up to above the x-axis where sine is positive. The sign of those angles are positive. All right, and so now I can use this sign chart to answer my questions. Let me distinguish here. All right, so y is concave up. I'm going to write CCU for concave up when the second derivative is positive. So this is on the interval 0 to pi and 2 pi to 3 pi. And also y is concave down when y double prime is less than 0. And that would be on the interval pi to 2 pi. Finally, y has a point of inflection at x equals anytime my concavity changed. So that was at pi and 2 pi. And those are our first 2 examples. Okay, we're going to learn another thing. This is called the second derivative test. You actually haven't done the second derivative test yet. That stuff in purple is not actually the second derivative. This material right here as the second derivative. So if f double prime is positive at a critical point, then f has a minimum there. All right, and let me try to explain what's going on here. What happens when f double prime is positive? Let's look at the chart. My chart tells me that when the second derivative, that's the third column here, is positive, then f prime is increasing and f is concave up. All right, so I have a function who's concave up. Also, I have a function that's concave up at a critical point. At a critical point. And so if f is concave up at a critical point, the critical point means that the derivative equals 0 or the derivative does not exist. And so think about concave up and then the derivative equaling 0, say. That would happen here. And so that's why f has a minimum. Conversely, let's suppose that f double prime is negative. So my second derivative is negative at a critical point. That means I'm concave down at a critical point. And so my function would have a maximum at that critical point. That's the second derivative test. All right. And this is going to be our final example. This is a graph of the picture, or this is a picture of the graph of the first derivative, And so when you read your chart, the information you're looking at is information about the first derivative. But my questions are going to be about f. So I want to know where f is increasing. Let's look at the chart. What is happening in f prime when f is increasing? F increasing, f prime positive. So you go back here, look at your graph, and you answer the question for where f is increasing. That is when f prime is positive. F prime is positive when f prime is above the x-axis. So that would be here and here. So let's say that's on the interval -4 to -1 and 2 to infinity. All right, you have 5 more questions here. Increasing, decreasing, maxes and mins. These are old questions. And then at D, I'm asking about concave up, concave down, and inflection points. Let me help you with the concave up for a second. So F is concave up. Going back to my chart here, F is concave up. Notice concave up is in purple. So analytically, if I had a function, I would take the second derivative. But I don't have a function, I have a graph. I have the graph of f prime. And it turns out that if f is concave up, f prime is increasing. So f concave up, f prime increasing. Go back to your question. F is concave up, that's when f prime is increasing. And my picture is of f prime. So now I look at the picture and I look to see where my picture is increasing. That would be from -infinity to, let's say, -3. And 1 to infinity. Okay, I'm going to leave the last 4 questions for you to answer.